Okay, guys, so this video might be a bit different than the other ones because I'm actually going to use all the difference. So this is to solve the HILT problem. And I'm not the one who really selected this problem, but basically it was a video online, which is this one here. I will provide all the links. So you see, basically it explains every single step, how to create the model. And it's very good, to tell the truth. He helped me a lot. And basically at the end, the problem is that this is the mix to show you how to calculate the reactions, but basically how to calculate the spring, see if I can find a problem that shows everything. Okay, so basically, we never see the whole problem, but basically the problem they're solving is this one here. Obviously, this is reverse. This is hold over here and you pull up, okay? And this is example given by FEMAP. It's not my problem. For the nonlinear solution for solution 401. So basically they simulate here the floor or the ground or the support with the springs, and they run the nonlinear solution 401. So just for me to learn, I follow this video, and you see that gives you a deformation of 0.162, but that's this time here. So actually it's 0.152, it doesn't matter, 0.162. That's about all the other, okay? All right. Then, like always, I like to have some type of validation. And if you go to this video, this will give you the analytical solution to find what is the value of the reaction force over here, all right? So basically, you go through every single detail. So I'm gonna save some time. And basically, this is, you have those two equations, you solve it for RBT, and let's see if it gives you the expression at the end. How it's gonna look like. All right, so basically you're gonna end up with an expression for this one, okay? So for the problem, for the data of this problem, which is this dimension and a vertical force of 5,000, all right? I did a quick MATLAB code, and that gives you a reaction force of about 11,563, okay? So this is the different models that I've done. And let me explain. So let's see, this is exactly the one that they have done on the tutorial, okay? So maybe here's easier to look at it. So basically, you see you have here a 5,000 Newton force. Here, this is pin, all right, around the hole, like it was bolted. And then the lower part is model with springs, okay? And again, if you go through the detail, you will see there is a function here, nonlinear function, that basically says that is zero when there's no displacement, but as soon as it moves a little bit, the springs become active when the displacement is actually positive. Okay, so when these start going up, the springs are going to start pulling down. All right, so if you do these calculations, all right, if I just go to this one, you see I get, okay, this is the von Mises stresses. That's not really what I wanted. So let me change here to total translation. I don't know why it's not showing total translation. Oh, okay, so basically it's not giving, oh, because I'm on the free body diagram. Yeah, the reason right here, free body diagram, you see before we had the 11,000, that was the reaction from the MATLAB. All right, we get about 10,550. This is good enough for me, okay? Let's see if this changes here, the value. Yeah, so if we go to 1, it's a little bit higher, 11,000, and the deformation would be 0.152. All right, so this is the one following the video, and I will provide the API file that they do not provide on the video on the support file. And before I forget, I always put everything into this website here. And if you go here, you should find all a bunch of my videos. And here you will have the support file. That's what I will put all these files, okay? Plus the API file. All right, so let's go back to this one. So here what I was surprised is this. I did this model and I said, okay, so this is basically to simulate what will be like if you had a base. So I said, okay, let me go and check, and I rebuild the same problem. So this is exactly the same problem, the 5,000 on top, at the bottom, but this time I replace the spring by a base. And if you want to look at the reactions, about 11,000, so that was good. That's my way to check. Full model, and I run everything. And you see again here, all right, I don't know which one. Obviously, the stresses are different, but I'm just basing everything on translation at this time. And this is because I'm on the free body, where basically you see the translation is 0.257. So I was like, okay, so how is it that here is about 0.152 running the nonlinear solution for one with the springs, and here I have 0.257. Okay, so I say, okay, so then I say, okay, let me run. This is solution 101, which is the linear solution. Now I say, okay, let me run the nonlinear solution with the, so basically the same problem here, but with solution 401. All right, so here maybe let me show you this. The only thing that changes here on the analysis, make sure you select this one, and then model, load, nonlinear analysis. Oops, I did not put it in here, looks like. All right, so maybe it's in here. Manage, edit, next, 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 next. Here, make sure you put these commands here, if that's not the defaults, and that you put these ones here. Okay, 0.01, 25 steps, 0.1, 20. This is basically almost the default that they use on the video. All right, and that's all I did. And basically here, what do we get the result? 0.154. Okay, let me maybe do it this way. All right, it's just because we are here on the free body. All right, that's not what I wanted to do. Anyway, it's 0.154. So this one kind of coincides with this one, which is the 0.152. So these two are very close. So that made me think, okay, so this is the linear solution. So what's happening? So why do they give so much difference? So next, what I did is, if you look at my other video for solution 106, is that I say, okay, so then it looks like the deformation of this bracket here, the L bracket, must be nonlinear, or must be due to large deformation. So what I did, let me pause the video for a second, and I'm going to open more files. Okay, so basically we have similar files, but this time, instead of having a load here of 5,000, it's only 500. All right, so now you see that this is the linear solution. So contacts, creating contacts with linear solutions. So model, connections. I mean, all these, like, again, I will provide this file so you can check them. So I get 0.025 cents. So right now the force is only 500. So I divided by 10. So now instead of being 0.152, it's 0.0257 using the linear solution. So I will do the same thing running the nonlinear solution for one. And you see that we get about the same, 0.0252. All right, so I say, okay, obviously this is due to the nonlinear deformation of this one. So in order to do it, I just took the problem, did this problem here. I have 5,000. And here, basically what you do is model, load. Again, I will provide all these files here. I don't know, so model, why it's not there, load. Okay, I thought it will be here, like on this folder here, but maybe I have it within the solution. So let's see. manage, edit, next. Okay, so let's see. So obviously I didn't use load set, so make sure you use these values over here, okay, before executing. All right. And now what we can do is we can go here to charting, create new data sets. Let's just say this would be deformation, vector set, output set value, total translation, location. Let's select just the middle node over here. So it would be this one, so 1. All right, value doesn't matter. And okay, that should be it. Oh, just put one value. All right, so I guess output set value, vector load set, total translation. All right, why is that putting all the values? Use all output sets. All right, let me see here what's happening. Okay, he only did it for one time step. All right, so I guess this is not the one I was. All right, let me pause and let me find out what is the issue for a second. Okay, so here we go. So yes, I had an issues because I thought I run it, but it had no convergence, so it stopped at just one time. So what I needed to do in the model was just to go to the model, load nonlinear analysis, and actually change this value here. I think I had 0.0001. It was non-convergent, so just change to 0.001 to this screen over here. You want, I can remove this one and see how we did it, but basically then the analysis is unchanged, is the number 10. I'm sure I did that before, but let's just redo it. Go here, next, and make sure you use this. And then once you run it, remember before we only had one, now we have 20 cases. So basically this is what it's doing, is breaking up the load of 5,000 into 20 loads, okay? And calculating for each one of the steps. So we can come here, and this is showing right away the figure, but let's say you don't know how to do the figure, but basically you see this is not a straight line, this becomes nonlinear. I was expecting to be more nonlinear, but I mean, it is what it is. Maybe if I make it bigger, it will show more curve. But basically you see that the behavior, the deformation of this is nonlinear. And that's why we obtain on these solutions here, the previous one, remember we had the 0.0252 for linear. Basically would be like if this line was going straight here, so we'll do a straight line. But you see that this value here would be lower than if it was just a straight line. All right, so what is the conclusion of all this problem is that when I started working on this problem and I did the one of the tutorial, which I find excellent. So I learned two things, is that when you do contacts, if you're going to do nonlinear contacts, or when you do the contacts, sometimes it might be smart to check if the solution is the behavior of your bracket would be linear and nonlinear. Okay, and that can be done with solution 106. The issue with solution 106 is that you cannot put springs, dependent springs. So this will have just one constant value, will not be in function of that. But I mean, when I did it in this case here, I did not put any springs. Okay, just to simplify the problem. I just wanted to see for which load it will become nonlinear. And you see it becomes nonlinear if you do a straight line pretty quick. I mean, like after the second load, so this is, let's say 5,000 divided by 20. So by 10 will be 500, 250. So each one of these one will be 250 loads. All right, so about 500, it becomes nonlinear, already here. All right, right after the second one. And also that will tell me is that if maybe if you need to run nonlinear contacts and the contacts can create issues, you can replace the contact just by the springs, okay? Because it should give you a similar result. And basically that would be the end of the video. All right, so again, I will post all the files into this website, including the API file that I mentioned in that video. And I hope this video was helpful. Thank you for your time.